So today we're looking at radicals as exponents. So when we have a radical, we have the index of the radical, which tells us the root, and we have the exponent. Okay, so this is a radical expression where we can, since radicals and exponents are essentially the same thing because they are inverses of each other, we can express them together. And the way we do this is this. We're going to express this as one exponent, where the numerator of the exponent represents the power and the denominator of the exponent represents the root. Okay, so I'm just going to highlight this. So we have our index here represented by the denominator and our exponent here represented by the numerator. So when we deal with radical expressions, we can actually convert them into exponential expressions and use exponent laws. And we can just use this as a rational exponent. So first things first, we want to make sure that we can actually show the radical as an exponential value. Okay, so we want to do that. So when we have this expression here, root 5, the fifth root of 7 to the power 10, okay, we can work this out and we can show this as 7 to the power 10 root 5. Now notice that since this is a fraction, we can actually simplify this fraction as a ratio. So essentially there's this property with exponents and roots in that if they're in proportion to each other, they will essentially undo each other, or they end up simplifying. Okay, so this ends up being 7 to the power 2, which is 49. Okay, now if you actually put this into your calculator, okay, if you do 7 to the power 10, 7 to the power 10, let's see here, just make sure. 7 to the power 10 is a really big number. It's 282,475,249. And if we express this as the fifth root, okay, if we want to do the fifth root of this, we end up with 49. Okay, so this is in fact true, and that this ratio of powers can be simplified. Okay, and I'll show you another way we can justify this. And looking at this as 7 to the power 10 over 5, okay, this can be written as power 5 power 2 root 5. Okay, and since 10 over 5 can be written as 5 times 2, we have, and the numerator represents powers, denominator represents the root. We have a power 5 and we have a root 5. And what do we know about power 5 and root 5? Well, they undo each other, or they cancel out. And this shows up as canceling in the ratio of a fraction. Now, they're not exactly the same thing, but they are reflected in the same way, and they share the same property, in that they can undo each other. Okay, so this power 5, this root 5 cancels out, and then we end up with 7 to the power 2. So anytime we have a rational exponent, we can simplify that, and those powers cancel out. So in fact, the fifth root is the same. We'll get rid of the fifth power, okay, because we have 7 to the power 5, so then we end up with 7 times 7. Okay, so that we can see that they will undo each other and they share similar properties, but this is reflected in the exponent here. Okay, so let's try this next one here. So this is 9 to the power 3 over 2 over 3. So to express this, the root is root 3, the power is power 2. Okay, so we end up with, this ends up being, if we want to work this out, we can calculate the value of this. This becomes the cube root of 81. Okay, so we end up with 327. The cube root of 27 is 3, and then we leave a factor of 3 in there. Here, be careful with this, and this is something that we have to start getting really careful with, because with algebraic expressions. Now, if we were to, we have to be very clear. Does the exponent apply to the a or the 2a? Okay. Now I see a lot of people, they will say, oh, we're just going to write this all as root 4 and power 5, something like that. And this is incorrect because this power only applies to the a. Okay. So we have to make sure that the 2 is independent of the power, and then we can put the denominator is my index of the root, it's root 4 and power 5. Okay, we're just going to leave it like that. Here we can, again, we have to make sure that the power only applies to the terms inside the radical, so that 3 is unaffected. This is going to be x. Well, it's got power 1 root 5. And then the y is going to be different because it has a different power on it. So we have to express it differently. So power 5 root 3. Okay. All right. So why is it that we can show that the fifth root of x to the power 10 really is x squared? Well, we can show this. We can show as a rational exponent and simplify it. Okay, so I can say that it's equal to x to the power 10 over 5, which then becomes x squared. So that's one way to do it. Another way we could show this is, well, we know that the fifth power and fifth root undo each other, so we can express this as x to the power 5. So x to the power 10 is really x to the power 5 times x to the power 5. And so what this means is that, well, that fifth root and power 5 will undo each other and we get just x. Okay, so there's x, and this power 5 and fifth root will give us another x. Okay, and then that gives us our x squared. So we can justify it in terms of the roots as well, roots and powers. We can justify in terms of a rational exponent. We can also justify in terms of roots and power. Notice that they're consistent. It is very important that we have consistency with that. Okay, so the ratio of powers and roots can be simplified. Okay, because we're talking about this groupings of things. Okay, we have power 10, root 10, and this ratio can be simplified. Here we have power 5 in groups of 5. Okay, and then we can show that the number of groups of 5 can be simplified in this way. So either way, we can do this. And in the end, it probably becomes much easier to deal with these expressions as an exponential expression and use a ratio of powers to simplify the exponent.